Hello, this is BricsCAD 3D. I'm going to be using it to model the metrology calculation. Do all the metrology calculations here in 3D. Okay, so if you've ever been on a ship, you kind of you get a metrology spreadsheet like this. Different ships, different metrology spreadsheets, different companies. So then what we do is we have three people filling in all the data, and at the very end we compare results. And if two guys get everything the same, we know that it's at least all the calculations are right and they filled in all the data properly. But often, like, you get one guy going in and doing some data cleaning here and he's messed up some formulas. That's him out. Another guy maybe has to got a bit distracted and filled in the wrong digicodes. They swapped RVs or something, I don't know. And final results in some way are different, and someone has to go back and check, and everything has to be cross-checked before this spreadsheet. It's kind of a report is handed over. I've never been a metrology party chief, but that's kind of how it's done. So the problem with Excel as well is sometimes you're having to think about something that's happening on the seabed, like installing a pipeline or a spool piece, and you're looking at it from up and down, and you're going, okay, that's north and that's south, and then you have now a KP or something that's increasing from north to south, so you're going up and down at the same time, and it gets confusing. I've helped people out actually where I've understood how the spreadsheet was relating to the physical objects and whether to add an extra zero point 0.5 centimeters to something or subtract it, something like that. Like someone has a look and they want to, what is this? Where is this plet? What is this pitch and roll? It's not very useful to someone who's thinking about the actual physical objects. So here we go. In my opinion, Excel is good for just you put in your raw data, you can see it, you can put colors to it, filters, sort it, clean it if you want. Other tools for cleaning, but it's kind of the everyone can operate it, so it's a good place. But what I have done instead, I've made this web page, Survey Forge. We have a prompt here. So we want to do a metrology calculation. So I want to get the structure heading, the inclination, data, the inclination and the direction of inclination from this raw data, which is, as you can see, some pitch and roll and heading. So I'm going to throw that in here. Okay, and this prompt here, it's running deterministic, rule-based. There's no AI behind this. It's recognizing from here what it needs to do, and it goes and does it. So here we have our data explorer. No results yet. All the data types from within the spreadsheet, some sample data, and let's run this prompt. Afterwards, you can export to a PDF or a docx, do whatever you like, put into a bigger report. So let's run it. There we go, our results. So some sample data at the top. So we've got our structure orientation, have our structure heading, our structure inclination data, which is the direction of the inclination, the heading, and the actual inclination from the Z. That's what we're looking at. Let's see how accurate it is. So here, some most relevant findings, assumptions, etc. But anyway, so what are we looking for? Structure inclination details, standard deviation on the pitch and roll stuff, the actual inclination degrees, which is small as expected for pitch and roll, and then the heading, 23 of the inclination is for 1. Okay. What about the structure heading? What was that? So that was here, the top. Structure heading 841. So this is structure heading here. Standard deviation. Okay, fairly small. So I'll put everything to 3 decimal places. We're just about, not quite accurate enough for that, but that's what I'll do. We'll get going with the, as promised, metrology calculations. So first of all, I'm going to load in this Spool metrology Lisp file. Then I'm going to run a load file command function within just to load up some initial data to get going quickly. Here we go. So here we have our field. There's a LBL beacon, the other LBL beacon in green, the baseline in cyan between the two, 11.139, and then the XY plane 10 with the heading and the inclination. And we're wanting to modify this structure here. So this would be a plem or a plat, and this would also be a plem or a plat over here, and then there's the 2 hubs, and the spool piece would go between the 2 here. So as you can see, all nice and visual, up and down being up and down. Right, in the Cartesian planes, the minus depth over here is below 0, and minus is negative is down. Okay, so let's have a look at this. So this is a inclination heading 45 and heading 45. So if we put it all up like that, move some of this out the way. What's nice about M leaders is they still point to what they need to point to, even if you drag them around. So here we have our baseline. Okay, we don't need to see what any of that is at the moment, so that's fine. This is very un-Excel. Okay, so there we have our heading, 45, and our inclination the same. So the structure heading and inclination are the same. And 20 degrees, which is about 20 degrees there. Okay. So that's quite a, you can see our structure's on quite a slope. You wouldn't be installing a plem or plate on 20 degree slope. Unless it had some special engineering. Okay. So let's edit this. Beacon and structure position, and well, not position, just the heading, inclination heading, and inclination. So that's 5 for heading. Heading with 45. Oh dear. And I'm going over here to get and then I'm going back here. Okay, so that is structure heading here, 4.841. Right, so this will swing the whole structure around. Anti-clockwise. Yeah, there we go. Right, now while I'm here, I'll change the inclination heading. That's 23.864. Making it sound easy. There we go. And inclination. That was 0.569. So let's watch the structure even out. Okay, there we go. And here are everything's updated and moved. And you can see if you remember, the digicourts depths have stayed the same and the position has stayed the same, because these are our results from the metrology. And those wouldn't change with the change in inclination. Right, so let's have a look. That's all nicely even. Let's drop this. Let's change the actual shape of the structure. The structure actually has a hub that is lower than that. Let's drop it. 2.5, 5, and instead of 3, I put 1. And there we go, and recalculated the inclination and distance for this. Hub A to hub B. Right, and then once you have all this filled in and the exact positions of the structures as you want them, then the engineer could come along and put in his models and orientate them with the base, the receptacle of the beacon receptacle and the hub, and this side too, and then with a couple digicort depths, minimum bend radius, you should have enough to design quite a good spool. And put the whole thing onto a digital terrain DTM, and you can have a look at the seabed and see if there's any potential little free spans, and off you go. Thanks for watching. That's my idea of how to do a spool metrology calculation. Please check and make sure it's all right.